Today we're going to be looking at floating point representation of decimal numbers. Now before you look at this, it's important you know how to do the 2's complement converting to binary, otherwise this won't make sense at a certain point. So before we get to converting decimal numbers, we're going to look at scientific notation and standard form. And versus normalized form and what the difference between them is. This isn't actually part of the course, I think it just helps to know, just because they teach it slightly different in maths and slightly different in computing. Before I came to the current school, I was in the maths department and they told me I was doing it wrong, and I taught the pupils the maths way and then kind of applied it to binary after that, but there's actually it's done slightly different in computing. So I've got some examples here. So if you were to get this question in maths or something like it, put the following number into standard form, what you would do is you would put a 4 there, and then you get this decimal point and you put it right after the first digit, and then you put everything else after it. And then you do times 10, and you count how many places you moved the decimal point. So you moved it up 3 places, and that's it. Now if you were to get the exact same question but it's in normalized form, so this is from a computing context, what you've got to do is you put a 0 at the start. I think it's actually easier because you can just remember to do that. You put a 0 at the start and then go 4, 4, 5, 6, 2, 2, oh god, and then you times 10, and you've bumped it up 1 extra place, the decimal point, so it's times 10 to the power of 4, and that's it. So that's what we're going to be doing as we move forward, so bear that in mind. There's going to be a 0 in the front. So here is what it looks like in the higher exam. So convert this number to floating point representation. There are 16 bits for the mantissa and 8 bits for the exponent. Now there's quite a few steps to go through. Maybe I should actually get the Word document up first. So the first step, is this it? Of course not. Oh no, it was, sorry. Right. The first step is that you put a 0 in front of the number, just like with normalized form. But you're not doing it by times 10, you're doing it by times 2 because we're working in binary. And then you count how many places you moved the point. From there, because you've got a 4 isn't a binary number, notice how the rest of it's in binary, you need to convert the 4 into binary as well. And then you've got to look at your mantissa and your exponent. So if it says a 16-bit mantissa, you need to make sure that bit is 16 digits long. And if it's, where is it? So it was only 12 digits to begin with, so you needed to add an extra 4. So this wasn't enough, before the times 2, this wasn't enough, so you had to add an extra 4 zeros. And then you need to make sure your 4, you can't just do a 4-digit number, well it's already 8 digits, so that's fine like that. Probably better just to show us off with examples. So I will get this, and first thing you got to do is put a 0 at the start, right? And then you do 1, 1, 0, 1, 1, 0, 1, 0. Now what we've done is we've moved the decimal point 4 places, so we're going to go times 2, and it's times 2 to the power of 4. Now I like to draw an arrow just to keep myself right and like keep it separate, and you need to turn this number into binary. So if you want, I mean it's quite a small number, so you can do, I'll do for this example, you can do your little headings. Most of them are going to obviously be unneeded, just so you know where this number is coming from. I mean, what's it going to be? Let's be honest. It's just a 1 and the 4 and nothing else. Usually they're quite small numbers. Then you've got to take this and count it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first bit said there are 16 bits for the mantissa. So the mantissa is this first number. We need to make it 16 bits long. So to do that, you actually just write I'll write it out again. You just need to write zeros until you get up to 16. So if we've got 9 so far, that means you have to do 7 zeros. And then you do times 2. And you have this binary number here. Now, and that's your answer. Now, you probably think when you're writing this out, it just looks wrong. Like if you did that in an exam, if you did that many zeros in a maths exam, it would be wrong, but that actually is what they want. Now, you don't get all the marks for that, just that. That's like the working bit. You'll get given a little grid like this you need to fill out, and the sign bit is whether it's a positive or negative number. And all you've got to do is take the first 0 and put the 0 there. Then, and this is the bit people mess up all the time, you just do the next 15 digits. You don't do the 0 again. So many people I think that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. Because we're sticking to a 16-bit mantissa, so many people add an extra 0 here and then keep the 0 here, and before you'd get the mark for this bit, you would lose a mark for this bit. So the 16-bit mantissa, the first bit is the sign bit, then the next 15 digits. Also, if there's anything, if you completely blank out on the day, if there's anything you're going to take away from this video, just put a 0 in the sign box. It's going to be 0. It's never going to be 1 in the exam. It's going to be 0. So if you take a complete panic attack, just write 0. I mean, it'd be great that you remember the rest and we can get the other marks here, but just write 0 no matter what in the sign box and you'll get at least 1 mark. And then the exponent here, well, you just chuck it in. Wait, is that right? Yeah, but I did too many zeros there, that's the problem, right? And that's meant to be a 0, not a 6. Right, so that's how it works. I've got another example. I realise, I know this video might be a bit long, but this is quite complicated, so I want to take my time with this. Also, there is a slightly different version of this, which I'll get to in a minute, but I just want to kind of do 2 of each version. So, right, let's do what we did before. We put a 0 in front. 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1. We moved the decimal point, let's see, 1, 2, 3, 4, 5, 6, 7 places. So times 10 to the power of 7. Right, so let's do that quickly. This would just be 0, 0, 0, and then it's 8, so 0 there. 4, 2, 1, all adds up to 7. That's your binary number for 7. Here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You don't have to add that many zeros with this one. So you would just do 3 zeros, and that's us up to 16. Again, and then if you wanted to, yeah, well, I'll do it. You do times 2, and then you write the number that we had up here. Right, that's the answer. So again, putting it in the box, like, what a shock, it's 0. It's always going to be 0. And then you do the next 15 digits. And I don't know if you missed this out. Would they give you the mark? I don't know. Just put it in the box to be sure. I mean, they're checking that you know the difference between the sign and mantissa. So, and then the exponent is 0, 0, 0, 0, 0, 1, 1, 1. Right. Slightly different example this time. This one starts off with a bunch of zeros after the decimal point. Now, normalized form, it wants a 1 to be right after the decimal point. So, although we've already got the 0, now we need to move these ones closer. So to do that, you do 0, and you get rid of these 4 zeros and just do 1, 1, 0, times 10. And now you're counting how many you got rid of. So we got rid of 4, so we write -4. Now, what you do with the negative 4 is you need to work out the same way we did with 2's complement, negative binary numbers. So we get regular 4, and then after that you flip the bits. This isn't worth any extra marks, by the way. It's still worth the same 1 mark for this. And then you add 1, and then you do your 1 plus 1 is 0, carry the 1, 1 plus 1 is 0, carry the 1, or if you like, I prefer, you just say, right, well the 1 plugs in there, the rest are zeros, and the rest of the number remains the same. For this bit, there are 16 bits, we need to make it 16 digits. So we've got 0, 1, 1, 0, that's 5. Then you have to write 11 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times 2, and that kind of joins up. We'll consider that joined up. And there's your answer. Again, the sign, what a shock, it's 0. And then just the 15 digits there. So 1, 1, 1. I'm losing my mind now. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. And then the exponent is just that bit there. Those are not meant to be L's, my apology, I don't know what happened. Right, 1, this is the last one, slightly different. There are 12 bits for the mantissa and 12 bits for the exponent. Now I haven't seen this come up yet, but then there's only been 1 exam and 1 specimen paper, but it could come up the way the question's worded, so we're going to be prepared for it. So, as before, and this isn't just for this type of question, it could be 12 bits here and 12 bits there, or 8 bits there and 16 bits for these ones. I think it's unlikely, but it could happen. So 0 point, and we get rid of the zeros, so there is 6 of them. So 1, 0 times 10 to the negative 6. And we need to get 6 in, or negative 6 in 2's complement. Now remember, it's 12 bits for the exponent, so we need to go 12 digits. Again, not meant to be an L, I don't know what's happening. So this would be 128, this is 256, 512, 1024, 2048. Not that it matters, but that's what those numbers represent. And then you negate it. What am I doing? Oh god, this is awful. 0, 0, 1, and then you add 1 as before. So 1 plus 1 is 0, carry the 1, and then you get 1 there, and the rest remains the same. For this side, we get 0, 1, 0, and now we've only got 12 bits to fill, so you don't have to do quite as many zeros, so we've got 8 more zeros to do. Times 2 to this. And there's your answer. Again, 0 for the sign. If there's one thing you take away, please just put a 0 on the sign. When it comes to prelim time and you're not putting a 0 on the sign, what are you doing with your life? Then just fill in this. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 adds up to 12, all this, that's fine. And then you fill in this bit here. Again, I don't know what's happening. Right, and that is how to turn a binary number with a decimal point into, to give it a floating point representation. It is a bit tricky, I'm not going to lie. It took me a while to get my head around it when they introduced it into the higher course. Practice will make perfect with this. Right, bye.